Polygons are the shapes of our world. Computer and television screens, doors, and sheets of paper are all polygons. Diagonals of polygons are also useful. We are going to learn how to instantly know how many diagonals any polygon can have. First, let's touch up on our vocabulary. What's a simple polygon? A simple polygon is any two-dimensional flat shape made only with straight sides that close in a space, and with sides that do not cross each other. A triangle is a polygon. A dart, kite, quadrilateral, and star are all polygons. Simple polygons can be concave or convex. The formula we will use works for all simple polygons. What's a diagonal? A diagonal of a polygon is a line from a vertex to a non-adjacent vertex. So a triangle, the simplest polygon, has no diagonals. You cannot draw a line from one interior angle to any other interior angle that is not also a side of the triangle. A quadrilateral, the next simplest, has two diagonals. A pentagon, whether regular or irregular, has 5 diagonals. In convex simple polygons, diagonals will always be within the interior. Consider a rectangular door. You can run a line from the top hinge corner to the bottom opposite corner. You can also run a line from the bottom hinge corner up to the top opposite corner. Those are the only 2 diagonals possible. In concave simple polygons, the diagonals may go outside the polygon, crossing sides and partly lying in the shape's exterior. They are still diagonals. Darts and stars are typical examples of concave polygons with diagonals outside their shapes. Do not attempt to apply these concepts and our diagonal formula to complex polygons, which are polygons with self-intersecting lines. Okay, now let's check out the diagonal of a polygon formula. To find all possible diagonals of a simple polygon with just a few sides, you can easily count them. When the polygon gets a bit complicated, counting them can be very hard. Fortunately, an easy formula exists to tell you exactly how many diagonals a polygon has. Remember that any vertex, corner, is connected by sides to 2 other vertices, so those connections cannot count as diagonals. That vertex cannot connect to itself either. So for n sides, we will immediately reduce the possible number of diagonals by 3. We also do not want to count the same diagonal twice. Our door, for example, only has 2 diagonals. You do not count going from the top hinge to the bottom opposite and back again. You will have to divide any answer by 2. This leaves us with an elegant formula, where n is the number of sides, or vertices. First, take the number of sides and minus 3, then times by the number of sides, then divide by 2. Let's test this formula on a pentagon with 5 sides. We take the number of sides, 5, and minus 3 to get 2, then times 2 by the number of sides, 5, to get 10, then divide by 2. A pentagon has only 5 diagonals. Our formula works. What about a tetracontachiheptagon, which is a ridiculously long but correct name for a 47gon? Once again, take the 47 sides, minus 3 to get 44, then times 44 by 47, then take that number and divide by 2. Trust the formula. A 47gon has 1,034 diagonals. This formula works every time to tell you exactly how many diagonals can be constructed inside or outside of any simple polygon, whether the shape is convex or concave. Lesson summary. You have learned a lot about particularly important parts of polygons, their diagonals. You now know how to identify the diagonals of any polygon and how to use the formula.